Hey everyone, and welcome to Chapter 9, Thermochemistry. In this chapter, along with Chapter 18, the other chapter in this unit, we are going to be talking about energy. We did this a little bit last semester at the very beginning. If you want to review what we have talked about in terms of energy and the exchange of energy and reactions, go back and check out Chapter E, the introduction, the essential chapter. That chapter gave us a brief introduction, but this chapter also does as well. It gives us a little bit more in-depth, but some of the terminology is done quickly. So if you have any questions about definitions or some of the basic first couple slides in this PowerPoint, go back into the essentials chapter and look up section 6. We're going to be talking about energy, work, and heat. Now, these three things are related. Energy is the overarching idea that it is anything that has the capacity to do work. Think of energy as something an object or a collection of objects can possess. Okay, it can be exchanged through contact. Example: collisions, when molecules react together. We don't just nicely hand atoms over to be bonded with other molecules. We actually collide the molecules. That's why stir bars are so great in the lab. They mix everything up and they make the molecules physically collide with each other. Now, energy is going to be composed of two different parts. The first part is work. Work is the force acting over a distance. Now, this isn't a physics class, but we are going to be talking about work being done by reactions or on reactions in this type of terminology, forces acting over a distance. Heat is the other component of energy that we will be talking about. And heat is the flow of energy caused by a difference in temperature. So whenever we think about reactions changing temperature, either absorbing or releasing some heat, that is going to be a component of the overall energy exchange in a reaction. So heat and work are two different ways that an object can exchange energy. And that energy can either go into a reaction or into an object, or it can either come out of an object. Now, there are two different ways to classify the overall energy. It can be kinetic energy, which is the energy of motion. Typically in textbooks, we always see billiard balls. I don't know why we think of pool, but it is a good way to imagine a ball rolling, right? Movement. That motion is energy being transferred into the energy of motion. Now, thermal energy is energy associated with a temperature change, okay? So if the energy deals with increasing or decreasing the temperature, it's specifically thermal energy. And then if the energy is consistent of motion, that is kinetic energy. Now, these two are related. Thermal energy is a type of kinetic energy, okay? Think about the motion of atoms. Now we see these billiard balls on the right-hand side. I'll just highlight this guy blue. As he's moving and he's going to collide with this purple billiard ball, the energy is transferred in the form of work. And then that's when the purple gets to continue on in the motion. Now, that type of kinetic energy, in motion energy, we can think about in terms of thermal energy with bonds breaking and forming. Another type of energy is potential energy. Okay, so this is different than kinetic or thermal energy. Potential energy is the energy that's stored up in an object, or the energy associated with the composition or position of an object. So we think about gravitational potential energy, right? If you hold a ball up in the air and you're holding it, there is the potential, right? There's gravity pulling down on it, but it hasn't yet been released, the ball. So the energy is stored in the structure of a compound, and that is potential energy. We will look at one type of form of this potential energy, which is going to be chemical energy. Chemical energy is associated with the positions of electron and nuclei. So think about the bond itself is a chemical potential energy. The bond is related to what is being attracted to it, the electrons and the nuclei, the protons, specifically in those nuclei. And it's not until that bond breaks that we have the thermal or the kinetic energy, right? So it's really this transfer between potential and kinetic energy, chemical energy, and thermal energy that we are going to discuss. I really like this chart because it shows you that relationship. And this is what we are going to really study this chapter is the exchange between the chemical energy, the energy stored in bonds, stored in the atom itself, stored in a molecule, and then how is it put into motion? How is that energy transferred to become thermal energy, the energy associated with temperature changes? Now, again, thermal energy is only one form of kinetic energy. We will see that there are some types of reactions that do not undergo a thermal energy exchange. But it's the best example that we can think of right now. Some more forms of energy. Electrical energy is a type of kinetic energy that is with the flow of an electric charge. We don't deal a lot with electrical energy in chemistry because our energy is dealing with the protons and the electrons. There is electrical charge within the electron itself. However, the electric energy that we're talking about here is more macroscopic in terms of electrical engineering. Heat or thermal energy is the kinetic energy associated with molecular motion, and this could be bonds breaking or bonds forming type of thermal energy. This could also be bonds vibrating. Think about your microwave. Your microwave heats up your food because it shines light from the electromagnetic spectrum, specifically in the microwave range, which is relatively low energy. However, it vibrates bonds and it makes them bend and wiggle, and that motion creates thermal energy, which heats up your food. Light or radiant energy is also a form of kinetic energy. It's associated with transitions in atoms. We saw electron excitation in terms of the emission spectra in last semester in chapter 2. We won't be talking too much about energy transitions of electrons. We're going to be mainly dealing now with reactivity and bonds and breaking and forming those bonds. Nuclear energy, super hot topic, especially because of trying to find alternate forms of energy, is the potential energy in the nucleus of atoms. So nuclear energy at its whole point, at its basic point, is looking at that potential energy. And chemical energy is what we are definitely going to talk about this semester. It's a potential energy due to the structure of atoms, the attachments between atoms, the positions relative to each other, etc. So these are the energy stored in bonds. Units of energy, we'll bring up all of our units of energy. One of the most important aspects that we need to remember from last semester is kinetic energy is equal to 1/2 mass times velocity squared. Now this is kinetic energy, right? And it's directly proportional then to an object's mass and velocity. So the faster the movement, the more kinetic energy. And also remember, temperature was proportional to kinetic energy last semester as well. When the mass is in kilograms and the velocity is in meters per second, the units of kinetic energy is called a joule. This is the primary unit that we will work with. Now, we do know that energy is a force over a distance. So that's where physicists and sometimes biologists, if you're into the kinesiology realm and you're doing biomechanics, like my husband does, he talks about newtons and Newton meters. I'm the chemist, I discuss the joule, but 1 joule is also 1 Newton meter, force over distance. So that is 1 joule is the amount of energy needed to move 1 kilogram of mass at a speed of 1 meters per second. Calorie is also used. Calorie is the amount of energy needed to raise the temperature of 1 gram of water per 1 degree Celsius. We will talk about the calorie when we get into calorimetry and specifically the food calorie and how are those food calories determined, what do they mean, and how does that deal with energy, right? And we'll get into that when we talk about calorimetry. But a food calorie, a big C calorie, is 1,000 little c calories. So 1 kcal is what we're talking about with 1 big C calorie. Guy smashes diamonds. I guess you could say he kilojoules. Gotta love chemistry cat. Yeah, I know. Here are some important energy conversions that we will be able to utilize throughout this semester. These are the conversions that you would need to know. You do need to know 1 kilocalorie is 1,000 calories, right? Because that is a prefix multiplier. All the other ones here you would be given because they are not prefix multipliers. They are actually unit conversions. But we will be using all of these unit conversions, so it's important to have them handy in practice problems. All right, we're going to talk about the first law of thermodynamics. Now, thermodynamics is this study of energy and its interconversion. That's what we're going to spend a whole unit talking about. And really, the whole semester is going to be based off of understanding reactivity now that we see in everyday life. So thermodynamics is the study of energy and its interconversions in reactivity. The first law of thermodynamics is the law of conservation of energy. You've heard the conservation idea before. We've had the law of conservation of mass. This should look very, very similar. It states that in a reaction, energy can neither be created nor destroyed, but it can be transferred. The energy in the universe is constant. It is conserved. Therefore, you can never design a system that will continually produce energy without some sort of energy source. So there's no such thing as a perpetual motion machine, right? Because you need to be able to supply the energy with that perpetual motion. Let's define a couple things that we have defined a little bit already, but we're going to define them again here in this chapter. A system is defined as the part of the universe, matter and associated energy that is being studied. This is primarily going to be our reactions that we talk about, right? The thing that we are looking at. Surroundings are going to be everything else outside. Typically, this is us as observers or as scientists. It could be our thermometer, it could be the air around the reaction, it could be the solvent that the solute, the reaction, is actually in, right? So it could be even smaller idea, as in if we have an aqueous solution, the solutes are the reactions and the solvent is the surroundings, okay? So we're going to get down to very nitty-gritty system surrounding labeling so that we truly know the energy exchange between the two. So when we see that energy can flow out of the system, that is going to be what we call exothermic. The energy of the system drops, the energy of the surroundings increases. This is exothermic. Energy flowing into the system, on the other hand, energy is put into the system, so the system energy is increasing, and then the energy of the surroundings is decreasing. This is called endothermic. Exiting the system is exothermic. The system, into the system, is endothermic. So we will base a lot of our reactions off of the energy flow from or to the system. And we need to be able to know, where does the system get the energy, or where does the system give the energy to? It's the surroundings. So energy is neither created nor destroyed. This is the first law of thermodynamics. When energy is transferred between objects or converted in from one form to another, the total amount of energy present at the beginning must also be present at the end. So you can see these little system gauges at the bottom right-hand side. The surroundings will gain the exact amount of energy that is lost from the system. So if we think about pushing down this ball on a spring, the spring itself is the system. So before we let go of the ball, we can think about the system gauge being right here. Let's just call this 2, right? Because it's the second mark. There's 1, there's 2, there's 3, there's 4. And the surroundings is just arbitrarily here at 1. Now, when we release the ball, and the kinetic energy is released from the system, from the spring or the ball itself, and movement is now being transferred out into the surroundings. Notice how the system dropped down 1 notch and the surroundings went up 1 notch. All right, that's how you would read these little gauge diagrams in your textbook. How we are going to be talking about this is delta E of the universe, the change in energy of the universe, is equal to 0. And that is overall energy of the system plus energy of the surroundings, okay? So if we said this was 2 and this was 1, right? This is now 1 and this is now 2. The change here in energy, 3 minus 3, is 0, okay? So before and after a reaction, the initial amount subtracted from the final amount is going to be overall 0 in terms of that change in energy overall. That doesn't mean the energy of the system can't change. It means that whatever the energy of the system changed to, the energy of the surroundings changed the exact same magnitude, just opposite sign. Internal energy. Internal energy is a special type of definition. It's the sum of the kinetic and potential energies of all the particles that compose the system. So this would be looking at the delta E of the system itself. The change in the internal energy of a system only depends on the amount of energy in the system at the beginning and at the end. So doesn't mean that it has to be 0, right? Because now we're just saying, hey, we're going to focus on the system only, the reaction, okay? So sometimes things are going to be written delta E of the system. SYS is kind of how I abbreviate that. You can write out the whole system as well. It means the same thing as delta E of the reaction. And that delta E is a state function. It doesn't matter how the reaction happens. It doesn't matter what pathway the reaction takes. All that matters is the beginning and the end conditions, not the process being used. So final minus initial, products minus reactants. This type of setup will be seen a lot in thermodynamics. We have quite a few state functions. Now, state function, just to be able to reiterate again what that means and what it does not mean. When we think about hiking up Mount Baldy. Mount Baldy is not too far away. I've hiked it many times with my husband. My husband and I went on one of our first dates hiking up Mount Baldy. He, as a kinesiology major, thought that I, a chemistry major, knew how to exercise. I did not, but I made it up the path. But all that mattered in thermodynamic term was I started at the bottom and then I reached that 10,000 feet elevation. Didn't matter how much crap I went through to get up there. It doesn't matter the path. If I went down a little bit, if I went back up, as long as I get there, the state function says initial and final. That's the difference that they are talking about in state functions. We will talk about this middle section. This middle section is important. It's called kinetics, how fast the reaction happens. At this point, we are only dealing with the thermodynamics, which is the initial and the final. All right. Just to sum up, The reactants have higher internal energy than the products. Energy of the system is negative. Energy flows out. This is exothermic. If we have the opposite, if the reactants have lower internal energy, then the delta E is positive and energy is flowing into the system. That would be endothermic. And the internal energy of the system can be treated in the same manner, energy flowing in or out based off of the sign of the delta E. Endothermic reactions, I studied them before they were cool. Nice. Energy exchange. Now we talked about heat, thermal energy. Now let's also see where work fits into this. Energy is exchanged between the system and the surroundings through heat and work. Sometimes some reactions only incorporate work. Sometimes some reactions only incorporate heat. We are going to look at both of these together. Q and W are how we abbreviate heat for Q, W for work. Q and W are not state functions. Their values depend on the process, okay? But they both can be exchanged between the system and the surroundings. Same type of sign work, just putting the words to this in table 9.1. This is a great table to start off with just to be able to verbalize the exchange. If Q, heat, is positive, that means the system is gaining the thermal energy. If Q is negative, the system is releasing or losing that thermal energy to the surroundings. W, same thing. Positive, work is done on the system. Negative work is done by the system onto the surroundings. Change in E, flowing in and out of the system, as what we already talked about. The energy exchange between the system and the surroundings, again, can be done either by heat exchange or by work being done, sometimes both. How do we quantify work? The first way is with pressure volume work. PV work is work caused by a volume change. Think about a reaction pushing against the system or pushing against the surroundings or pushing on the system, all right? So we're looking at the ability of gases to expand, right? Pretty much this is going to be with reactions that are involving gases, things that actually produce pressure and have a specific change of volume. So as long as the external pressure is kept constant, we can see pressure volume work. The calculation is work is equal to the negative P delta V. Pressure is constant, and delta V is the change in volume. Volume final minus volume initial. Yep, you guessed it. It's a state function. So multiplying the negative pressure times the change in volume will get the work. Now that would be in atmosphere liters, right? That's in this unit, not in technically a unit of energy. So we need a new conversion factor. This conversion factor will always be given to you. 101.3 joules is equal to 1 atmosphere times liter. Let's just do a quick example. You're going to inflate a balloon for a back to school party because you're so excited to be back in school. If you inflate a balloon from a volume of 0.100 liters, so let's just go big or go home, 1.85 liters is our new volume, right? I'll say this is V1 and V2 against an external pressure of 1 atm because we're all at atmospheric 1 atm sea level. How much work is being done in joules? All right, so work is equal to negative P delta V. Negative 1.00 atm times delta V. Let's go ahead and see what that is. Give myself some more room. Final minus initial. This is very, very important to make sure we're final minus initial here. That way the sign of work is correct. Don't forget that negative sign in the front of the calculation. It is extremely important to make sure that we are identifying the correct signage here, because that will tell us whether work is done on the system or by the system. All right, so we should be getting 1.75 ATM liters. We then want to convert that into joules, all right? Joules. Times it by 101.3 joules per 1 atmosphere liter. 177 joules. Again, 3 sig figs. How did I get 3 sig figs? Do this first, 1.75, multiply it by that, 3 sig figs times the unit conversion factor, which is an infinite number of sig figs. I'm ending with 177 joules. Now, don't forget your negative. Negative 177 joules. That means work is done by the system. Well, let's imagine, what is the system? The system is the balloon itself. The balloon, after getting more air, is expanding and pushing out, making the volume larger. It's pushing out onto the surroundings. That is work done by the system